Let's suppose we have this curve r equals f of theta in the xy plane, and we're interested in finding the area bounded by theta 1 and theta 2 and the curve. So this region right here. So this is the region we're interested in, and we want to know what is the area of this region. So the region is bounded by theta 1, theta 2, and this curve r equals f of theta. So the way you're going to do that is by using a definite integral. So this area, it's going to be defined as the integral starting from theta 1 to theta 2 of 1/2 r squared d theta. So that's the integration formula we're going to be using to find the area of a polar region. So if you want to rewrite r squared in terms of theta, you can also write it as, this is the integral from starting from theta 1 to theta 2 of 1/2 f of theta squared d theta. So let's go ahead and see if we can do some problems using this formula to find area of polar regions. All right, so we're going to find the area of this polar region right here. So let's go ahead and sketch, because the sketching will help you to identify theta 1 and theta 2 and how does the region looks like. So here's our xy plane. Now, if you're not familiar with how to sketch polar curves, I'll leave a link in the description box for you to check it out. So this is a polar curve in a form of some a minus b sine theta. So since a is greater than b, this is going to be a Limacon. And it's going to open along the, or it's going to be facing along the negative y-axis. So this is going to be a Limacon. So let's graph it. So when theta is equal to 0, our r value is going to be 2. So let's say this is 2. When theta is pi over 2, sine of pi over 2 is 1. So 2 minus 1, that will be a 1. So perhaps it's right here. And then when theta equals pi, our sine value is 0. So 2 minus 0, that would be at 2. So this is going to be at negative 2 right here. And then when theta is 3 pi over 2 down here, our sine value is negative 1. So 2 minus negative 1, that's 3. So we're going to hit this point. And then when theta is 2 pi, sine of 2 pi is 0. So we're back to 2. Right, so that's the shape. And we are interested in finding the area inside this Limacon. So what is the area of this? So we're going to set up the definite integral as follows. The area, it's going to be the integral from theta 1 to theta 2 of 1/2 r squared. Well, r is this formula in terms of theta. So this is 2 minus sine theta squared d theta. Now, theta 1 is the first point where the region starts, and theta 2 where the region ends. You end your region. So we're going to start right here and then go all the way around and end right here, which means theta 1 is going to be 0, starting from 0, go all the way around. Theta 2 would be 2 pi. So those are the limit of integration. Now let's go ahead and integrate this so that's not too difficult. So we're going to go ahead and use some identities and simplify this. So this is equal to, I'll plug the 1/2. We're integrating from 0 to 2 pi of 2 sine theta squared. If you expand that, you'll have 4 minus 4 sine theta plus sine squared theta d theta. Now let's just bring that down here so we have more space to work on. So let's keep writing the 1/2 outside the integration. This is 0 to 2 pi. And now I'm going to go ahead and replace this with an identity. So sine squared theta, recall that you can replace that with 1/2, 1 minus cosine 2 theta. So that's what I'm going to replace right in here. So our integrand becomes 4 minus 4 sine theta. And now replacing sine squared with this identity. So that's plus 1/2 times 1 minus cosine 2 theta d theta. Now I'm going to go ahead and distribute this half out, so it simplifies the work a little bit more. So this would give you 1/2 and then cosine 2 theta over 2. Now I'm also going to go ahead and combine these because they're like terms before I integrate. So you want to simplify as much as you can before integrating. So we have 1/2 outside, 0 to 2 pi, 4 plus 1/2, that's 9/2, minus 4 sine theta, minus cosine 2 theta over 2 d theta. So I forgot to write that here. This is d theta. All right, now we're ready to integrate this. So the integral of 9 over 2 respect to theta, that's going to be just 9 over 2 theta. The integral of sine theta will be negative cosine, so the negative in front of negative 4 will cancel. That'll be plus 4 cosine theta. And the integral of cosine 2 theta will be sine 2 theta over 2. So this is minus sine 2 theta over 4. And we're going to take it from 0 to 2 pi. All right, so this is looking good. Now let's plug in the upper limit of integration and minus the lower limit of integration. So this is 1/2 times 9 over 2 times 2 pi, plugging in 2 pi for theta, plus cosine of 2 pi minus sine 2 pi times 2, that would be 4 pi over 4, minus, now plug in 0. When you plug in 0 in here, that's 0. So which means this is 0, then minus 4 cosine of 0, and then minus sine of 0 over 4. All right, so we plugged in the lower limit of integration. Now let's simplify this. This is 1/2 times 9 over 2, and the 2 cancels, so we can simplify that further as 9 pi. Now here, this is going to be 1, so this is just 4 times 1, that's 4. Sine of 4 pi over 4, that's 0. And then cosine of 0 is 1, so minus 4. Sine of 0 is also 0. So now these terms will cancel out. Our area will simply be 9 pi over 2. So that's the area of this polar region. All right, so here's the next problem. We're going to sketch this polar equation and then find the area inside one petal. So this is a graph of a petal. It looks like a rose petal. So it looks like a flower. So here's our XY plane. We'll try to draw it first and then find the area. So if you have right here, if you have an n times theta, or let's say 2 theta in this case. So what this number tells us is the number of petals you're going to have. So here, if this is 2 theta, you're going to have 2 times 2 petals. So in other words, you will have 4 petals for this particular graph. So how do we know where our each petal is going to be? Well, whenever this function has its maximum, sine has its maximum at pi over 2. So where will we have our first petal? So we know at pi over 2, sine has its maximum. So when theta equals pi over 2, you will have the maximum value for sine. So I'm going to take the argument 2 theta, set it equal to pi over 2. So that will give us theta equals pi over 4. So that's where your first petal is going to be, first petal. Now you want to find where's the next petal. The next petal, it's going to be, the way we're going to do that is find the distance between each petal. So we know the entire circle right here, it's 2 pi. So that's period for sine. So you take the period 2 pi divided by the number of petals. So in this case, we'll have 4 petals. So we take 2 pi divided by 4, that'll be pi over 2. So what pi over 2 represents is the distance between each petal. So once you know where the first petal is, then you just add that distance to get to the next petal. So I'm going to put all of these ideas together and draw. So first petal is a pi over 4. So we know pi over 4 is right here. let's suppose this is pi over 4. So our first petal is right here. The second petal, it's going to be pi over 4 plus pi over 2. So that would be somewhere right here. So pi over 2 plus pi over 4, that would give you 3 pi over 4. So this is where you're going to have your next petal. And then next petal will be 3 pi over 4 plus pi over 2. So that's right here. That's about 5 pi over 4. So that's the next one. And then the last petal, it's going to be 5 pi over 4 plus pi over 2. That's 7 pi over 4. So it's going to be right here. So there you go. That's your picture. Now we want to know what's the area of one petal. So let's say I want to know just the area of this petal right here. What is the area of this one? Because it's easy to work with. It's in the first quadrant. So this area, it's going to be equal to the integral 1/2 r squared. Well, r here is 4 sine 2 theta squared d theta. But what about the limit of integration? Well, where does the petal start and where does it end? So if you look at the picture, it starts right here at 0, and then it goes around and it stops right here, which is at pi over 2. Now, another way to see it is you want to see when does this function comes back to 0, this function. So we know sine theta, sine 2 theta is, we want it to be 0 because that's when it's going to come back to the origin. So we want 2 theta to equal 0. So that's the first point of intersection. That means theta is equal to 0. So that's your lower limit of integration. Next one will be, when is this next time sine is 0? The next time sine is 0 is when it hits pi. So we want 2 pi, 2 theta to equals pi, because that's when sine of that theta is 0, which means theta is equal to pi over 2. So that's your next limit of integration. And that's how you find it. You find your first starting point and the second ending point. So that's the integration limit, 0 to pi over 2. It's clear to see it from the picture, but that's how you would do it algebraically. All right, now we're ready to integrate. That's not too difficult. So this is equal to 1/2, pull it out, from 0 to pi over 2 of 16 sine squared of 2 theta d theta. So here again, we're going to use the identity we used earlier. So we know that sine squared of 2 theta is equal to 1/2 1 minus cosine of 2 times 2 theta. So then I'm going to replace that up here and integrate. So we have the area is equal to, now 16 and 1/2, that's 8. So we have the 8 of the integral from 0 to pi over 2. And sine squared 2 theta, I'm replacing it with 1/2 1 minus cosine 4 theta d theta. And then 1/2 and 8, I can simplify those into 4. So we're integrating 0 to pi over 2 of 1 minus cosine 4 theta d theta. Now this is straightforward. We know this integral of 1 is theta. Integral of cosine 4 theta, that's sine 4 theta over 4. We're going to take it from 0 to pi over 2. And now plug in the upper limit of integration. This is 4 times pi over 2 minus sine of 4 times pi over 2 over 4. Minus, when you plug in the lower limit of integration, you'll get 0. Now this right here, this is sine of 2 pi, because 4 times 1 pi over 2, that's going to give you 2 pi. Sine of 2 pi is 0, so this is 0. So all of this simplifies to just 4 times pi over 2, which is 2 pi. So there you go. That's your area for one petal of this curve. All right, so I'll practice some more examples and be comfortable with area of polar regions. See you next time.